Hey students, so this is Mr. Volts here, talking about minerals. We're just going to do a brief introduction here. This is the presentation that I gave here on class earlier this week. So, beginning off, the very beginning, we have the building blocks of everything. We start off with atoms. And when you put a couple atoms together, then you end up with elements. Then after you have elements, if you put two or more elements together, you end up with a compound. Now, it doesn't necessarily have to go in this order because yes, gold is an element, but it is also considered a mineral. And gold is not a compound because just by itself, it is a mineral. So some do bypass this step, but I want you to keep in mind that elements put together create compounds. And oftentimes when you repeat those patterns over and over and over and over again, you then end up with a mineral. And later on we will talk about rocks, but right now just set that off to the side. So the building blocks again go from atoms to elements, compounds, and minerals. So what are minerals, how do they form, and how can they be identified? Students, you're going to find this on page 142 and 145 of your textbooks. That's going to be Module E that you have, the dynamic earth. So what do all minerals have in common? The characteristics that all minerals have is that they are naturally occurring. They are inorganic, meaning that they weren't formed from anything that was living before. They have a definite crystalline structure, which basically means that all the way from the atoms building up and up and up and up, building up over time, you have a crystal that is built up from that. And wherever you take a sample from that mineral, whether it's on the top or the side or the bottom, the chemical composition is going to be the same. So these are four characteristics that all minerals have. And also, just a side note, with this naturally occurring piece at the top, you may say, well, wait a second, can't we make diamonds? Absolutely. But here's the deal. If you ever have a mineral that you can only make in a lab, that can't be considered an actual mineral. So it's a very important point to consider. And also coming back down here to definite chemical composition, students, because they are the same chemically throughout, we technically consider minerals to be pure substances, and we'll get into that in a little bit. So, okay, you may be thinking, how long does it actually take a mineral to form? Well, if you maybe think about your own life, if you know, think about how old that you will live. And so, I hope to live to be 80 or more years old, and, maybe even beyond. But if you think about minerals, they take millions and millions of years to form. So if I'm off here to my left and I'm mining some iron, and I go off and do my business and I use that iron for something, and then that gets broken and I throw it away. If I come back to that same exact spot over here to my left 20 years, 30 years later, that iron isn't going to grow back. Okay, it's going to take millions of years to form again. So we consider minerals to be non-renewable resources. And students, this is one of your power standards that I can describe how minerals and fossil fuels take millions of years to form. So keep note of how important this is for us. Here, this is where I want to talk a little bit about pure substances and mixtures. So do you remember how before what I said about minerals? Yeah, minerals are pure substances. And if you look here, pure substances, usually inorganic, definite crystal structure, same, oh, excuse me there, definite crystal structure, or usually same chemical composition throughout, that's pure substance. So this is all the category when we talk about minerals, and they can't be made of rocks. Mixtures, however, can sometimes be made of organic substances. They don't have a definite crystal structure because they're all jumbled up, not the same chemical composition, and they can be made of minerals. One way to think about this, students, that may be helpful, is if you've ever made chocolate chip cookies and you maybe think of a full chocolate bar, like a Hershey's chocolate bar sitting right next to it. Well, when you take them and you set them side by side, your mixture is going to be your cookie dough with some chips here, some flour here. Maybe it still isn't all mixed up all the way. It's all together. It's all kind of mixed. It's not definite structure throughout, not the same chemical composition throughout. But a pure substance, like a chocolate bar just by itself, it's going to be the same throughout. So minerals can be considered our chocolate bars, and mixtures or our rocks can be considered our cookie dough. So what changes the size of a crystal of a mineral? If you imagine for a second two tables, each table has the same number of blocks, let's say 1,000 wooden blocks on each table. And I have two teams, and I say, okay, teams, you're competing against each other. And on one table, you guys get 30 seconds to build a giant cube out of all of these little cubes. And this other table over here, with the same number of cubes and the same number of people, I'm going to give you an hour and a half. Now, you may be saying, Mr. Volts, this is really not a fair competition at all, and I know. But if I give them that amount of time, and I say after 30 seconds, all right, team, you're done, but I give this team over here an hour and a half, if you think about how big their structures are going to be, let's think about that for a second. How big are those structures going to be? The one over here on the left-hand side is actually going to be a lot smaller, right? It's going to be maybe only 2 or 3 cubes tall, maybe not very wide. Whereas this one, after an hour and a half, is going to be 6, 7, 8, 9, 10, maybe 12 cubes high and 12 cubes wide, and quite a substantial structure. The same thing goes with minerals and when they're forming. Minerals that have small crystals or that are really small and short, they cooled fast. They did not have very much time. Okay, just like the side over here. They didn't have much time to create their structure. However, the table over here had a long time. They could go slowly with it. So they were able to create a large crystal or a large cube with their smaller cubes. This information you'll find on page 148 as well as 150. Now there's 6 different tests that we use in order to figure out what a mineral actually is. We test its density in order to see how much stuff is in the amount of space that there is. Remember, that's grams over centimeters cubed. Do you remember? To be a heartbreaker, in order to figure out this formula, you take a heart and you cut it in half and you have mass divided by volume. Another one is hardness. It's testing the ability of your mineral to scratch a reference mineral on a scale. It's called the Mohs hardness scale. And when your mineral is scratched, the reference mineral is as harder than your mineral. So if your fingernail scratches that mineral, okay, you know that it's softer than your fingernail. But if it scratches your fingernail, you know it's harder than your fingernail. Streak you find by rubbing on a white tile, and it's not always going to be the same color as the mineral, but all samples should have the same color. So for example, hematite is one mineral that we look at, and sometimes it's brown, sometimes it's got a little greenish hue on one side of it. It can be a lot of different colors, but when you rub that on a white streak plate, it's always going to be that characteristic darkish reddish brown color. And that's more reliable than just looking at the color of a mineral, because sometimes they can oxidize sitting out in the air, and that'll change them to look a different color. The cleavage, if you think about meat cleaver, which was one of those big, long, square knives that butchers use in order to cut up meat, they cut through a straight line, and so you can think of this as a mineral breaking along a flat surface in a straight line. And fracture is the tendency of a mineral to break along irregular or curved surfaces. And so if you think of a piece of quartz or anything that's like kind of like the example of quartz that I have in class up at my desk. Okay, it's kind of irregular looking, and if you haven't seen it, you can come up and take a peek if you are still confused about fracture. When anything's broken along curved edges, that's what fracture looks like. And luster is the way that a mineral reflects light, and this includes whether it's metallic or glassy, whether it looks like a pearl, if it looks like there's glass that has a little grease on it, that's vitreous, or if it's submetallic, like the graphite that comes out of your pencil. In students, that wraps up our introduction on minerals. Following this, you should be doing the mineral identification test in class, and then later on, you'll be learning about rocks and mining as well. So stay tuned.